All right, let's jump right into this explainer. If you're a focused learner looking to completely demystify databases, you're in exactly the right place today. We're going on a structured zero to advanced journey through the ultimate landscape of SQL, structured query language. We've taken the raw foundational mechanics and transformed them into a clear, actionable roadmap. Our goal here is to create a zero to advanced SQL question set covering all the questions you really need to know, taking you from writing your very first query all the way to optimizing massive enterprise-level systems.
But first, think about this. What actually separates a beginner who can pull a few rows of data from a true database master? To figure that out, we're framing this explainer as a simulation of a high-stakes technical interview. We are covering all the essential questions that mirror exactly what you'd face out in the real world. We're going to level up your skills step by step, breaking down the absolute most complex concepts into direct, understandable takeaways. Here's our roadmap to mastery for today. 1. The SQL basics. 2. The power of joins. 3. Intermediate data manipulation. 4. Advanced scenarios. And 5. Performance and optimization. Section 1. The SQL basics. Laying the relational foundation. Okay, here's your first classic interview question. What is the actual difference between delete, truncate, and drop? Well, delete is a row-by-row operation. It meticulously logs every single row it removes. Now, that makes it slower, but crucially, you can perform a rollback if you mess up. Truncate, on the other hand, deletes all your rows incredibly fast, but there is absolutely no going back. No rollback is possible. And finally, drop, that's the nuclear option. It doesn't just delete the data, it wipes out the entire table structure from the database. Fastest execution, but total permanent destruction. Next up is a famous trap. Where versus having. This trips up so many people. So the where clause is a row-level filter that applies before any grouping even happens. You're going to use this with standard select, update, or delete commands. Having, however, is a group-level filter. It kicks in after the group by clause has done its thing, which is exactly why it's exclusively used with aggregate functions, like when you're calculating averages or sums. Think of it like this. You filter the raw data with where, you group it, and then you filter those grouped results with having.
Section 2. The power of joins, connecting the dots.
So, the absolute most common way we connect data is the inner join. It strictly returns matching rows from both the left and right tables. Think of a Venn diagram. An inner join represents just that middle intersection. If a record in the left table doesn't have a corresponding match in the right table based on your condition, it just gets completely ignored. It strictly returns the overlap. So what does that actually look like in code? Here is your basic syntax. You're selecting your columns and then stating inner join table to. But the absolute beating heart of this query is the on clause at the very end. On table 1, common column equals table 2, common column. This right here is where you declare the relationship. That condition literally has to be true in both tables for the row to show up in your final result set. Now, while joins connect tables horizontally, what if we want to combine result sets vertically? That brings us to another great technical question, union versus union all. Both operators combine the results of 2 or more select statements into a single column list. But here is the critical difference for your performance. Union automatically hunts down and removes duplicate records. That requires extra processing power, making it slower. Union all, though, keeps all duplicate values. The database just blindly stacks the results, which makes it incredibly fast. So if you know your data won't have duplicates, or you honestly just don't care if it does, always reach for union all.
Section 3. Intermediate data manipulation, elevating your queries.
Think of a subquery as simply asking a question inside of another question. It's essentially a nested query that you use as a condition to dynamically filter your main dataset. The database engine, let's say MySQL, runs the inner query, figures out that answer, and then passes that result directly to the outer main query. It's just a phenomenally powerful way to make your code dynamic instead of relying on static, hard-coded values. When you start writing massive, complex queries, you're gonna need temporary workspaces to hold intermediate results. You basically have 2 main choices here, temporary tables and common table expressions, or CTEs for short. Temp tables use actual physical storage. Because of this, you can use them multiple times in a single session, and you can even add indexes to them. They are fantastic for heavy reuse. A CTE, however, exists only in logical memory for a single use within that exact query. It vanishes immediately after. The golden rule: Use temp tables when your data needs to be reused multiple times, and stick to CTEs for short-term data manipulation to keep your code super clean and readable. Okay, this next feature is a literal game changer for data analysis: window functions. Remember how we talked about group by earlier? How it collapses your rows into a single summary output? Well, a window function performs calculations across related rows, like assigning a row number or a rank, without collapsing the results. Your individual rows stay completely intact, but they now have this incredibly powerful calculated column running right alongside them, determined by the over clause. It is an absolute massive level up for your SQL toolkit. Section 4. Advanced Scenarios, Logic and Data Integrity. This next concept brilliantly illustrates ACID properties, which is all about ensuring reliable processing by using a transaction block. Take a look at this logic. We begin a transaction, update an employee's salary, and then we create a save point named SP1. After that, we make a second update, but wait, what if something goes totally wrong with that second update? Well, we don't have to scrap the whole thing. We can just issue a rollback to SP1. This lets you safely undo partial changes without blowing up the entire transaction before you finally issue a commit to permanently save the work. As an advanced user, you aren't just going to write queries. You'll be writing reusable logic that's stored directly on the database itself. But you've got to choose between a stored procedure and a function. A stored procedure is built for the heavy lifting. It can perform data manipulation language or DML operations like insert, update, and delete, and it handles all your complex business logic. A function is way stricter. It cannot perform DML operations, and it absolutely must return a single value. Basically, use procedures for actions and functions for calculations. Section 5. Performance and Optimization, the boss stage. All right, the absolute most crucial takeaways of this entire explainer come down to these optimization best practices. First, you must create indexes strategically on the columns you use in where and join clauses. Second, stop using select star. Seriously, only pull the exact columns you actually need so you can save memory. Third, for massive data sets, swap out in for exists, because exists actually stops checking the moment it finds the first match. Fourth, be sure to use limit or top to cap your results. And finally, whatever you do, avoid wrapping columns in functions inside your where clause. Doing that forces the database to evaluate the function on every single row before it can even touch an index. But here's a thought. How do you actually know if your query is fast before you run it in a production environment? Well, you pull back the curtain on the database engine. If you're in SQL Server, you can use Set Show Plan All on right before your query. This generates a beautifully detailed roadmap showing exactly how the engine plans to retrieve your data. It reveals the execution order, the types of joins it's going to use, and exactly where your bottlenecks are hiding. Now, if you're using MySQL, the equivalent is the explain keyword. By simply typing explain before your standard select statement, the database won't actually run the query. Instead, it outputs its execution plan. This is exactly how the masters optimize. They read this plan to see if their queries are actually using those strategic indexes we just talked about, or if the database is quietly being forced into a sluggish, terrible full table scan. Finally, to optimize effectively, you have to understand your battlefield. Are you working in an OLTP or an OLAP system? OLTP stands for Online Transaction Processing. This is for your day-to-day lightning-fast operations. Think of an ATM processing a cash withdrawal. It requires high consistency and very small, very rapid queries. OLAP, on the other hand, is Online Analytical Processing. This is your massive data warehouse used for historical data analysis, where you're running complex aggregations over millions of rows. The optimization techniques you choose depend entirely on which of these specific architectures you're actually building for. So, we've gone from basic row deletions all the way to analyzing the internal execution plans of database engines. You've got the roadmap, you know the functions, and you understand the underlying architecture. So I'm going to leave you with this final, provocative thought as you step out of this explainer and into your next technical challenge. Armed with these strategies, are you ready to optimize a massive, totally unindexed data set containing millions of messy, real-world records? Because all that data is out there, just waiting for a master to command it.